Hey everyone, we're going to start learning about systems of equations and how to solve them. We spent last class learning how to write systems of equations from word problems, but today we're going to start solving them. The way we're going to solve these systems is to solve them by graphing. We will learn about two other ways called substitution and elimination in the coming days, but today we're going to worry about solving systems by graphing. Now that being said, starting today, when we say go to Desmos, we're not just talking about regular Desmos.com anymore. We need to practice using the Desmos that we're going to be allowed to use on the STAR test, which means we need to go to desmos.com/practice. Okay, bookmark this instead of regular Desmos now because we need to be practicing with the one from STAR. What will happen is that you will go to desmos.com/practice. It will show up something like this. You're going to choose assessment because we need to pick the STAR test. After that, it's going to come up with a place that you need to type in Texas or STAR so that we can pick the one that's approved for the STAR test. Since we are grade Algebra 1, we're going to choose this last option for grade 8 Science, Biology, grade 8 Math, Algebra 1, Algebra 2, that graphing calculator. Then you'll say Start Practice. This will just ensure that you're practicing with exactly the tools that you're going to get on the STAR test. So let's watch me do that. So I'm going to go to my web browser, and instead of just regular desmos.com, I'm going to type in desmos.com and then finish it off with /practice. Okay, like I said, you're going to click choose assessment, and then you're going to type in Texas or STAR. It will come up, and we say start practice. It should look exactly the same as regular Desmos, except now in the top left-hand corner it says Texas STAR. Okay, this is the one that you'll be able to use on the STAR test, so we want to make sure we're practicing with the correct capabilities. Now, today's lesson, we're going to be using Desmos to check our work. This is actually playing on some prior knowledge that you have from 8th grade. You've learned about this before, but let me remind you. If we want to find the solution to a system of equations, remember a system of equations is two or more equations graphed on the same coordinate plane or existing in the same situation, we have three types of solutions we can have. In this first example right here, you learned about this one in 8th grade. You see that the red and the blue line have an intersection point? That means that this type of solution has one solution. And it's going to be the x and y coordinate that correspond exactly to where they cross. Okay, so we can kind of decide that the solution to a system of equations is the x and y coordinate that make both equations true. It's their intersection point. The second example here in the center, this should look familiar to us. What kind of lines are these? What kind of lines is the red and blue line? How are they related? Yeah, hopefully you notice that these are parallel lines. And you also know that parallel lines are never going to intersect. So they can't have an intersection point, which means they're going to have no solution. That is their type of solution. The third option here looks kind of funky. If you notice that there's only one purple line, and that's because we had a red line graphed and a blue line graphed right on top of it. If we were looking for intersection points, we could say it intersects here, and here, and here, and here, and all of these crazy points on and off the graph. Well, that's a lot of coordinate points. In fact, it's an infinite amount of solutions. Infinitely many solutions is what we're going to call this one when they have so many places that they cross that they're right on top of each other. I'm going to let y'all shorten this to IMS for infinitely many solutions. So if you write IMS, I understand you're talking about it crossing everywhere in an infinite many times. Okay, so let's check and make sure we understand this. On the first four examples here, all we're trying to do is see how many solutions they have. Not where they are, but how many solutions do the following systems of equations have. Okay, easy question. How many solutions means how many times do the two lines cross? Very obviously, in the first system, these two lines cross once, which means this has one solution. Great. In number 2, It's saying that there are two lines. It's saying, like in the one that turned purple for us, it has a red line that goes through it and then a blue line that goes through it. So essentially they're like right on top of each other. So they cross here and here and here and here and everywhere in between. This has an infinite amount of solutions, infinitely many solutions. Do the third system, do those lines cross at all? No, these lines don't cross at all. There's no place where they have corresponding values that make both equations true, so this has no solution. Lastly, if we look at number 4, we have the equation y equals 2x plus 1 and y equals 2x minus 5. There's two ways I want you to think about this. What do you notice about the slopes of these two lines? These are the same slopes. They're the same number. And if they have the same slopes, don't you remember that the same slopes means that these things are parallel? These two lines are going to be parallel. Parallel lines never intersect, so this system also has no solution. But if we weren't 100% sure that that is correct, what we could do is we could take this system and we could type it into Desmos. Y equals 2x plus 1 and y equals 2x minus 5 and visually check that they have no intersection point. These are parallel lines and no matter where I look, they never intersect. They have no solution. Great. So now that we know what we're looking for, let's go ahead and solve some systems by graphing. The questions are going to say, what is the solution to the following system? Remember, that's the key word right there to let us know we are looking for the x and y coordinate that makes both equations true, essentially where the two lines intersect. So we're going to review our graphing information. We know that when we're graphing, we need a slope and we need a y-intercept, but we have that from y equals mx plus b. So we're going to begin the first graph at 2 and have a slope of rise 1, run 2. Rise 1, run 2. We do that until we can draw a super straight line. Grab a straight edge or a piece of paper or something to really draw a straight line on your notes. And voila, here's our first line. In the second equation, I'm still going to need a slope and a y-intercept. The slope is negative 1 over 2 and the y-intercept, or the beginning value, is 4. So I plot that on the y-axis. This means for the slope of negative 1/2, I'm going to go down 1 and over 2. Down 1 over 2. Until I feel confident that I can draw a nice pretty straight line across this graph. Put some arrows at the end. And then look for a graphical solution to this system. But we're just looking for the coordinate where these two lines intersect. That's right here. Those two lines, the red, or the, wow, I know my colors, the purple and the green line intersect at the coordinate point 2, 3. That's the address or the coordinate where that line shows up. We would start at the origin, count to the right 2, and up 3. That's the coordinate or the address of that point. And that is the solution to this system. That's the x and y value that if I plugged into both equations would be exactly true. Let's have you try one. Okay, number 6 is for you guys. I want you guys to pause the video and try graphing this system to find its solution. Here's what my system looked like when I graphed it. So I know that this has a solution and that the solution is going to appear right here where the two lines intersect. That is the coordinate 3, 2, which means 3, 2, that coordinate point represents my solution, over 3, up 2. That's graphically where they intersect. That means that is my solution. But let's say you just weren't sure about the slope and y-intercept of both of these lines. Let's say that's not a strong suit for you. Please go ahead and check your work. So if we hop over to Desmos and we type in our two y equals mx plus b equations, we can see that they graph just the same as we see on our graph by hand, and that Desmos will show you a coordinate point that you can physically click with your mouse. when you click it with your mouse, it's going to show you a coordinate point that is their solution. 3, 2 is exactly what we got as the solution when we did this by hand. Fantastic. A couple things I want to point out to you about number 7. We're going to do this one together. When we graph lines, we have not been graphing them from standard form. We've been solving them for y and graphing them in y equals mx plus b form. So are both of these equations in a form that I can graph right now? No, we're going to need to solve these equations for y. But don't worry, we've been doing this for so long, this should feel super simple. We're going to take the x to the other side, cross the line, change the sign. We write everything down. And we're going to divide by the number in front of y to each and every part of that equation. So much so that I see that the y is equal to 3 over 2x minus 3. Now I know my slope and I know my y-intercept, and I'm able to graph this. We start at -3. We're going to go up 1, 2, 3 over 2, 1, 2, 3 over 2, until I can draw a straight line and create my first part of this system. My first line, first function, first graph of this system. The second equation I'm also going to need to solve for y because I don't currently know how to graph this in standard form. So we follow the same steps. Take the x to the other side, cross a line, change the sign, then we write everything down. What number is currently in front of y? Good, yeah, we're going to divide by -1 to each and every piece of this equation so that I have y equals 2x minus 3. But now I know my slope and I know my y-intercept. My slope is 2, which is the fraction 2 over 1, but I'm going to begin at the y-intercept of -3. That means with the slope going up 2 over 1, up 2 over 1, up 2 over 1, I have this purple graph that I'm going to use a straight edge to graph on my same coordinate plane. Where does the solution to this system appear? Yeah, hopefully you notice that this solution to this system appears right here. That is the coordinate 0, -3. 0, -3 is the coordinate pair that is the solution to this system of equations. We've done 3 examples so far, and in each of them we have just graphed the equation, written it in y equals mx plus p and graphed it, and then checked our work on Desmos. Let's make sure that we're correct, okay? This is why I really wanted you to pull out Desmos test mode, which is what we're going to call this one, the practice one. Because right now, if I were to try to graph the first equation without solving it for y, do you notice that this little triangle is going to say plotting implicit equations and inequalities is disabled? Which means that for the STAR test, Desmos will not be able to graph standard form functions, but it can graph their solved versions when we solve them for y. So y equals 3 over 2x minus, not 6, Miss Quigley, minus 3, equal to y equals 2x minus 3 is what we got when we solved these equations for y. And they have a solution at 0, -3, like we thought on our graph. The last example on your notes today is actually really cool. This is a real-world example of why you would want to even know how to solve systems of equations. It's going to tie in what we learned last time about writing systems of equations and what we learned today about solving them. This says, 2 customers went to a post office to buy postcards and large envelopes. Seems normal. We do that. We go to stores and we buy stuff. Each postcard costs the same amount and each large envelope costs the same amount. The first customer paid $4 for 2 postcards and 1 large envelope. The second customer paid $8 for 6 postcards and 1 large envelope. The question here says, what is the cost in dollars of each postcard and each large envelope? So we need to know what the cost in dollars is for a postcard and an envelope. That means that's what I currently do not know. And since I don't know what they are, that's going to be my variables. The cost of the postcard and the cost of the envelope. It is of the utmost importance that you label your variables when we're doing real-world problems. You'll see why at the end of this question. Let's digest the information we were given. In the red part that I highlighted, it says the first customer paid $4 for 2 postcards and 1 large envelope. Well, I already said that postcards is going to be X and large envelopes is going to be Y. So we can see that the red sentence translates to the mathematical equation 2x plus 1y is equal to $4. And again, in the green sentence, because postcards is X and envelopes is Y, we can see that the green sentence translates to 6x plus 1y equal to 8. But I don't just want to write this equation, I want to solve it. I want to be able to graph these two lines, see where the system intersects so that I know what the solution or the cost in dollars of each postcard and each large envelope is. So I know I need to solve these equations for y because I'm going to have to graph these things. Okay? So we're going to solve the first equation for y, cross a line, change the sign. We'd have 1y equal to negative 2x plus 4. If you feel the need to divide by 1, go for it, but if you know dividing by 1 doesn't change anything, you can skip this step. Y equals negative 2x plus 4. Okay, here's my first equation that I'm going to graph. The second equation that I'm going to graph is 6x plus 1y equal to 8. But again, I need this to be in y equals mx plus b form. Cross a line, change the sign. 1y equal to negative 6x plus 8, divide by 1. And I would have y equal to negative 6x plus 8. Here's my second equation. So let's graph these things on the coordinate plane. Okay, the first one, the red equation, has a y-intercept of 4. So I'm going to start this equation at 4. It has a slope of negative 2, which means I'm going to go down 2 coordinates and over 1 before I grab a straight edge of some sort and graph this line. There is the first customer's mathematical representation of their trip to the store. The second equation has a y-intercept of 8, there's 8, and a slope of negative 6, which means I'm going to pop down 1, 2, 3, 4, 5, 6, and over 1. 1, 2, 3, 4, 5, it's off graph, that's fine. So I'm going to grab my straight edge and connect the dots between these green equations. We would see that this has a solution. We know that this system that's talking about the postcards and not envelopes has a solution because they have a place that they cross in the real plane. That, my friends, is the coordinate 1, 2. Now in a math problem telling me, Miss Quigley, parentheses 1, 2, close parentheses is the solution would be fine. But remember, the question I'm actually asking you here was what is the cost in dollars of each postcard and each large envelope? Well, we said the postcards are going to be X. So if we look at this, we have a 1 in the X spot. And we said that each large envelope was going to be Y. And we have a 2 in the Y spot of this coordinate. Which means that I know that postcards cost $1 and large envelopes cost $2. And now I've answered the question in real life. I know exactly what each the postcard and the envelope cost at this post office. And that's the beauty of solving systems of equations, is that we're going to take real-world examples of things that we know, things that we don't know, put them into math, and pull them back out as real-world things. Like I said earlier in this video, you can always check your work for these systems on Desmos. So once you solve them for y, if you're not confident in your graphing or you just want to check your work, you can always throw the system into Desmos and double check that your output of your intersection point matches what you've graphed. See y'all in class. Can't wait to solve systems with you.